Right, good afternoon, everyone. It's just coming up to 2 o'clock in the UK on Tuesday, the 6th of October. Hopefully, everyone is just starting to join the meeting now, and I can see some attendees queuing up and starting to participate there. So, as is typical with these webinars, people often run back to back from one meeting to another, as it's just turning the hour now to 2 o'clock in the UK. We'd like to give people a few minutes to finish one meeting and have time to jump over and join the next. So please bear with us. Thank you for those who joined promptly and on time. It's always welcome, but everyone in the real world has to allow for a little bit of flexibility for people to join. So while we're waiting, and I'll say this again in another few minutes to let people catch up, we're expecting to take about 30-40 minutes of presentation here, and while we're presenting to you today, standard housekeeping procedures for these webinars, I'm sure you're used to it. We'll have everyone in the audience on mute. If you've got questions while you're listening, please come and ask them. Use the Q&A button in the tool here on your web browser. Don't use the chat button, that doesn't work on these. So you'll hear some people from our team speaking about the technology and its applications today, but do ask questions in the Q&A channel, because we've got our engineers on standby to answer your questions live if possible, and if not, of course, let us know in the Q&A if you'd like us to follow up with you afterwards. Sometimes the questions get very complex and they deserve a more thorough answer offline, and it's difficult to sometimes answer everyone. Certainly last month's one was like that, and we had sort of 20 or 30 parallel conversations that we were trying to help everyone with. But that's a good problem. So as I mentioned, people are just starting to come in now to the attendees room, so you will be on mute. And today we are going to be discussing with you the subject of enhancement of protection of complex circuits, particularly wide area protection applications, and how our technology is rather well suited to enable differential protection schemes for multi-zone or multi-ended complex circuits, which has actually already been the case in the field. We're going to have Dr. Neil Gordon, Head of Sensor Technologies, talking to everyone about how this technology applies in this case, how it's being used, and also some practical examples showing some of the sort of technology advantages that Synaptec's distributed electromechanical sensing platform offers. That's not only limited to the protection functions, but some of the other upgrade paths that are availability by installing it. And then when Neil's finished, like I said, he should take about 25 minutes to actually go through the slides. We've been learning that very often there's about 10 minutes worth of Q&A time that we have to give at the end, because people ask more and more questions. And we'll try and capture the most relevant ones and popular ones and play them back here at the end, because sometimes a single person will ask a very useful question and other people would appreciate hearing the question and the answer to it. So we'll try and make sense of that as we go along. That should take another 10 minutes at the end, and typically these things take about 45 to 50 minutes, depending just how popular or complex it is and how many questions are being asked. Now, at the end, there is some slides here with all of our contact details and a reminder about how to get in touch with us through different media and platforms and social media and our website. We will keep the webinar session open at the end, just in case people do need to overrun and ask more questions. But after we've finished, we try to record these sessions and then make them available again later on for other people to use. And a lot of the material we're talking about is available on our website already. That's Synaptec with the dot between the T and the E, where you can find our application notes and case studies. So I think we're not getting too many people through more now, so it's probably time for me to stop and introduce Dr. Neil Gordon, who's going to take you through the main part of this. And as I say, do please use your Q&A button and ask questions of the engineers as we're going along, and then we'll review them all together at the end. Neil, over to you.
Okay, thank you, Saul. Hopefully everyone can hear me okay. So as Saul says, my name is Neil Gordon. I'm the head of sensor technologies at Synaptec, and I'm going to take you through the application of our technology to differential protection, particularly focused on wide area, multi-ended, multi-zone, complex circuits generally. As Saul's mentioned, I'll just reiterate it. If there are any questions, please do ask these in the Q&A section on Zoom. We have engineers there available to reply, and we can address any specific questions that come up or any repeated questions that come up at the end. So I'm going to start today with an introduction to the company, after which I'll take you through our technology and its specific application in differential protection and how that pertains to wide area or complex multi-zone and multi-terminal circuits. So Synaptec is an instrumentation company. We're based in Glasgow in Scotland, and what we've done is we commercialized for the first time a distributed electrical sensing technology. What this means is that we're able to use the existing fiber optic, which is embedded already in, for example, the underground cables or subsea cables offshore, or in the optical ground wire in overhead lines. And we use that fiber not as a telecoms medium, but as a means of transmitting analog measurements of electrical parameters. Now, the ability to measure electrical parameters passively over long distances and at multiple locations is unique to Synaptec, and it allows us to provide high quality point-on-wave measurements of current and voltage at unprecedented speed, range, and price when compared to alternative or traditional measurement technologies. And this means that it's particularly well suited to providing simplified protection instrumentation for complex circuits. The first applications of the technology have been in the terrestrial transmission sector. And you can see along the bottom of the slide here some of the clients with whom we've worked already over the last few years, including some major TSOs in the UK and Scandinavia. And in the last couple of years, our first foray into the offshore sector with the offshore renewable energy catapult in the UK and with Vattenfall. We're also backed by Williams, the UK F1 company, and their advanced engineering team, who bring us expertise in mechanical engineering as well. So the installations that we've covered to date, which are summarized on this slide, they cover really a wide range of applications from protection to automation, control and condition monitoring. But today, as I've said, I'll be focusing upon deployment of this system for wide area, multi-terminal and multi-zone protection instrumentation. So first, I'd like to just start by explaining some of the unique capabilities of this technology and generally how that makes it well placed to be used in the power sector. I'm not going to go into a lot of detail on how the underlying technology works, but I would say if you're interested in how that operates and kind of the background to the sensing technology that we use, as part of this webinar series, our managing director, Philip Orr, produced and delivered a webinar on this a few weeks ago, and a recording of that should be available on our LinkedIn and via our website as well. So first of all, fundamentally, what the company does is we deliver completely passive sensor networks. What that means in practice is that we can very securely deliver high quality electrical measurements over a wide area, and we can backhaul these back to a central location at the speed of light without requiring any supporting infrastructure at each location like auxiliary power supplies, GPS access, telecoms networks, etc. So already you're stripping away a lot of the complexity which is normally associated with a traditional measurement scheme. And once you have this high quality synchronous data available at a central location, this allows you to operate robust differential protection schemes over a wide area without the complex infrastructure that's normally associated with such a scheme. Now, quite a unique aspect of this technology is that you have that high quality, that synchronized point-on-wave data available at a central location. So this means that beyond serving that data to traditional protection relays and performing conventional protection architectures or informing conventional protection architectures, what we have is an instrumentation system that will centrally deliver granular data from a very wide area. So beyond simple protection applications, it can also be expanded and used to improve visibility and to inform smarter asset management decisions. So broadly, this means that we can reduce the capex and, more importantly, the complexity associated with more conventional electrical protection schemes, as well as streamlining OpEx by enabling more granular and smarter decision support without compromising the accuracy, the speed of measurement, the quality or the robustness of the measurements from a conventional scheme, nor compromising the security of the operator's data, which is important. So the real thrust of the technology is this, that compared to other measurement technologies, we can reach more locations over wider areas with reduced complexity and less auxiliary equipment. And hopefully that's what I'm going to convince you of over the remainder of this presentation. So hopefully that's at least whetted your appetite as to the power of this instrumentation scheme and generally how it's well suited to power networks applications. So I'm going to move on now to address the topic specifically of wide area or multi-terminal protection and the challenges it poses that Synaptec's technology can directly address. So integration of new distributed energy resources at both the transmission and the distribution level frequently requires connection into an existing circuit. Now, approaches to this will vary around the world, but it's not uncommon, at least in the US and the UK in particular, for this to result in circuits with 3 or more ends to that circuit, which lend themselves to particular challenges around electrical protection. Even in other territories where this is not necessarily the way these connections are made, any complex multi-zone circuit can be addressed in a similar way by this technology. Now, differential protection is, of course, the gold standard in electrical protection because it gives the operator complete confidence in the location of the fault inside or outside of a protected zone. However, in these kind of wide area or multi-zone or multi-terminal situations, it can be overly complex and expensive. Because it relies on multiple discrete measurement schemes and protection relays that are in constant communication over packet networks. So a common fallback to avoid that complexity and that OPEX is to use distance protection, which requires less instrumentation hardware, but can lead to ambiguity about fault location because it's essentially working out an estimate of the distance to that fault. And that can be particularly problematic for multi-zone or multi-terminal applications where you need to know the zone in which that fault is located. So generally, there's a number of drawbacks which apply to both distance and line differential systems. So as I've said, for instance, the infrastructure to support them can be very complex, requiring multiple powered units all talking to one another over packet networks. Because there's variable latency in these packet networks, accurate time synchronization can be quite challenging. And also, there are particular concerns about deploying teleprotection over these networks, thanks to that variable latency. And from a purely practical perspective, if you want to install new measurement schemes, there's implications around physical space, weight, and the requirements for civil works at the installation location. So while the industry always wants to deploy robust differential protection because that gives you the kind of gold standard protection of that electrical circuit, there's a clear need for a simplified instrumentation scheme and a scalable instrumentation scheme that allows differential protection to be deployed on wide area, multi-terminal and multi-zone circuits. But it should also retain the reliability of existing methods. So what I'm going to do is I'm going to move on to explain how Synaptec systems directly address that need. So in describing this system, I'm going to consider a simple three-ended system like the one you can see in front of you just now. This is, as I've said, quite typical of circuits in the UK and the US, where you might even go up to 3, 4, or 5-ended circuits. And while it might be less prevalent in other territories, depending on the philosophy of the operator or the regulator, hopefully you'll see that this system is very flexible and is readily extensible to other types of complex circuit beyond this simple example. So as I've mentioned in the introduction, our measurement system uses the existing fiber in the power network, like in the optical ground wire, to communicate analog measurements of electrical quantities back to a central location. What this means is that in any one of our differential current instrumentation schemes, we require only 2 different hardware components. The first is a receiver at one end of the fiber, and the second is each of the discrete sensors which are installed or daisy-chained along that fiber. The receiver in that system is the Interrogator, which you can see an example of here on the screen. This is the only powered and time synchronized device in the scheme, so it's ordinarily installed into the protection and control rack in a substation environment. It's a 3U and 19-inch rack unit, which receives all the sensor signals delivered over that existing single mode fiber network and outputs digital measurements in something like the IEC 61850 format, for example, to the process bus, so that the measurements are interoperable and can be consumed by devices like protection relays from all the major suppliers like GE and ABB and Schweitzer. The second element, the second hardware element in the system is the sensor. So one Interrogator can support a very large number of remote sensors which are distributed along that existing single mode fiber in the network. And for protection applications, for differential protection applications in particular, the sensor would be Synaptec's photonic current transducer, or PCT, which an example of is shown on the screen just now. So this consists of an industry standard iron core current transformer, but the secondary side of that is optically instrumented by a passive current sensor. So this means that the design is very simple and very familiar in form factor to a traditional CT. The only difference being that rather than having copper secondaries out of that CT, you only have safe single mode fiber entering and leaving that device. And while the example you can see here would obviously be installed around an insulated cable, for example, for an air insulated application, we would obviously install this on top of an appropriate standoff insulator. And again, only safe optical fiber would be entering and leaving that device. And then those remote sensors are then used to form that differential or unit protection network. Now, one important factor I've not touched on yet is the range of this system. So each of these sensors can be installed at distances of up to and beyond 100 kilometers from the Interrogator, depending on the quality of the existing fiber network. And this reach is unique among other electrical instrumentation technologies, so it lends itself particularly to applications in wide area and multi-zone sensing. So I'm just going to move on to drill down a little deeper into the advantages that this brings to differential protection for this type of multi-zone, multi-ended circuit. So first of all, the system is very simple compared to conventional schemes. As I've said, we don't require power supplies, time synchronization, or active telecoms at any of the remote measurement locations. Also, no non-standard installation processes are required, meaning that the installation procedure is very quick and very familiar to any installer in the industry. It's simply mounting of a standard current transformer, which is of course a standard process, and safe and simple single mode fiber splicing, which will be very familiar to any telecoms trained engineer. Because the fundamental measurement technology allows passive optical measurement of the CT secondary, we can of course either install a full primary connected device incorporating the primary CT, or if required, we can retrofit to the secondary of existing conventional CTs, effectively digitizing those over a long distance. The system is also very robust, so each sensor has a very wide operating temperature range over which the sensitivity of that sensor to a current is very stable. And the optical sensing method using single mode fiber is immune to electromagnetic interference, even over the unprecedented long distances available to this technology. Because we have very accurate knowledge of the time of flight in the fiber, each measurement is not time-stamped where the measurement is taken, but is actually time-stamped centrally on receipt of the measurements by the interrogator. This is actually particularly powerful because it means that while GPS access is not required at the remote locations, it also means that all sensors will retain relative sync because they're all measured by the same interrogation scheme, even in the event of loss of GPS. So when you consider that the protection scheme will continue to operate effectively even when GPS is lost, or if there's any power loss at remote locations, that's quite a powerful prospect. So the entire protection scheme remains intact and operational, even in the event of loss of time sync or loss of power at those remote locations. Furthermore, the instrumentation network is very secure. So because the measurements are encoded in analog light, there is no data actually outside the substation. The measurement data is only produced once inside the operator's estate, back in the substation, and the sensing network is impossible to hack or spoof because of this. Because of the simplicity of the installation and the scalability of the scheme, it's possible to deploy more advanced protection schemes. So you can see now what I've shown here is that we can instrument the T connection like this. So normally if you were to instrument the connection point, that would necessitate building of a substation at that position to provide the auxiliary power, the GPS receivers, all that supporting infrastructure that's conventionally required. Because our systems are completely passive, we can instrument that point without requiring essentially a substation to be built at that location, immediately enabling discrete multi-zone differential protection from a single end without that those civil works, that complex infrastructure, that initial outlay to achieve that. So what I'm going to show you next is a case study which directly shows deployment of this type of multi-ended protection scheme with a transmission system operator in the UK. So we're currently engaged with a major UK TSO to deliver a simplified protection scheme for a three-ended transmission circuit using a system very similar to that I've just described. In this scheme, what we have is three-phase current monitored at 3 locations, so that's 9 current sensors in total, and they are distributed over a total distance of 50 kilometers. And as I've said, no power was required at the remote measurement locations. Timestamping of all those measurements is performed centrally at the interrogator, and therefore no GPS access is required at those remote locations. And this means, again, that even in the event of total loss of GPS access, all the sensors retain relative sync and the protection scheme remains operational. You can see some particular parameters of this installed scheme on the right-hand side here. And here you can see some of the equipment actually undergoing factory acceptance testing in Glasgow before installation. Now this system, as I described previously, was secondary connected to existing protection class CTs at each measurement location, which is why our sensors are just deployed in these small form factor, light rack mount type devices in this case. And you can see them next to the interrogator sitting here on the bench. But it's of course important to stress that we can provide, and we do provide, complete primary connected devices as well. Now in this installation and as part of the testing to support this installation, the interrogator was tested to ensure it could receive data from all 9 current sensors over that total distance of 50 kilometers. And it publishes measurements in the IEC 61850 standard. So we were able to prove interoperability of the system with protection relays from GE, ABB and Schweitzer engineering laboratories. And we were able to prove compliance with the instrumentation, communication, and time synchronization standards as well. So it's fully tested against all the standards you would expect of this type of instrumentation technology. Now, as part of this work, the TSO with whom we're working has examined the business case for this technology. And what they found is that this scheme represents significant reduction in cost, but more importantly, in the complexity of circuit protection, because it eliminates the need for multiple protection relays and telecoms. It simplifies time synchronization of all measurements in the protection scheme, and it facilitates faster installations that require minimal civil works to install. So in total, the TSO's own case study estimated that this scheme would save them £250,000 for each installation of this type, compared to conventional protection architectures. And if you want to read any more about this specific case study, that case study is available via our website, to which I'll provide links at the end of the presentation. So that was a quick run through of that case study, but it shows a very simple and powerful application of the system in a straight replacement of traditional instrumentation architectures to enable that wide area multi-terminal differential protection. There are also some advanced functions that we can enable for this system, and I'm going to cover a few of those on the following slides as well. So the first of these is intertrip replacement. So the idea behind this is that we can take the system one step further by completely eliminating the separate active telecoms channel that would normally be required to deliver the intertrip signal from the protection scheme to any remote breakers in that circuit. So Synaptec has the ability to deploy simple and robust controllers, which are integrated into the that we use to obtain the current measurements. So not only can we receive measurements over a wide area using this system, using the already installed single mode fiber, but we can also use that fiber channel to transmit a basic control signal. So these can be used to issue simple commands to a remote plant, such as tripping of breakers in response to fault detection. And since this requires no separate comms fibers or telecoms equipment, it enables a further reduction in the complexity of the differential protection scheme compared to traditional instrumentation methods, and also simplifies some of the associated issues with variable latency in those packet networks. Furthermore, the system is also uniquely scalable and upgradable. Each single interrogator can support up to 50 passive single-phase current sensors over a nominal distance of 100 kilometers of fiber. This means that a single interrogator is capable of monitoring up to 16 three-phase locations, which again is unmatched by any other measurement technology that we are aware of today. This means that the system is scalable to very complex multi-terminal and multi-zone circuits, while keeping the instrumentation scheme that monitors and protects those circuits as simple as possible. Now, additionally, the way this system works is that it makes available synchronous, high-quality point-on-wave data at the interrogator, so at a central location for every sensor in the network. So even beyond the simple differential protection applications that I've discussed so far, this can also be used to provide the operator with enhanced visibility of the state of their network by providing that granular data from each one of these remote measurement points back at that central location. So what this all means is that while Synaptec's passive sensor networks are well suited to delivering protection instrumentation over wide areas or complex circuits, in which traditional differential protection schemes are overly complex and distance protection is not sufficiently accurate, And given that that scheme is uniquely scalable, robust, and simple to deploy, it can also provide this additional functionality which would not be available to a conventional system. So just to stress that by its nature, what this system does is it delivers high quality, high sample rate measurements at that central location. And that's what allows these powerful protection architectures to be realized. But this means that beyond this relatively straightforward protection application and without requiring any hardware upgrades to the system, a wealth of information about the state of the power network can also be delivered to the customer. Because we have these synchronous and real-time measurements from every sensor in the array, this can enable powerful additional benefits, things like analysis and categorization of fault type, wide area multi-point measurement of power quality or centralized delivery of synchrophasors, or detection of oscillatory behavior over wide areas. All of these can be enabled by delivery of that point-by-point data at that central location. So on top of the dedicated hardware that we use to deliver measurements to differential protection schemes to replace those conventional schemes and make them much simpler, we can also deploy software visualization and analysis tools like the one you can see on the screen here, which will allow the operator to make the most of the wealth of data that's generated by that instrumentation network and enable enhanced visibility without the additional hardware installation or configuration that you might need with other schemes. So in summary, Synaptec's technology provides an affordably scalable, distributed and secure instrumentation scheme for power networks and assets. When applied to this specific application of wide area multi-ended circuits, it's particularly well suited to providing instrumentation for differential protection. This is precisely because the technology allows us to reach out to more locations over wider areas with reduced complexity and less reliance on auxiliary infrastructure when compared to other instrumentation types. Our sensors they're optically instrumented CTs, so they're reliable and familiar to installers, and they're also very safe and quick to install. All of which makes the technology ideal for multi-point, wide area, complex protection of power networks. And finally, beyond that protection instrumentation, the system can be upgraded with no additional hardware to deliver high quality point-on-wave measurements from that wide area to a central location, giving the operator advanced visibility of that network and supporting smarter asset management. So I hope that's been very useful for everyone. There's a lot of additional information on this available on our website, including application notes, technical information, and case studies. So I would encourage you to look at that if you have any particular interest in any of these topics that have come up. So I guess now I'll pass back to Saul, and he can let me know if there's any particular questions that have come up during the course of the presentation. Thank you.
That's great. Thank you, Neil. Appreciate that. Spot on time as ever. So just coming up to past, we said would be 20-something minutes, and it was. That's great. We did have some technical questions here, and I know Lloyd's been trying to sort of answer live while we're going, but let me just replay them for the group because, you know, like I said, sometimes these have general relevance. So one of them was, okay, can you talk a bit more about the delays during the event of fault and relay operation? So is there any delay? And what are the kind of response times we're talking about here for our system?
Yep, of course. So we design our system and test it against the standards required of the industry instrumentation standards. So that would be IEC 60044 or the new 61869, which requires us to sample each of our measurements and publish the measurement data within 2 milliseconds to be consumed by protection relays. And we comfortably meet that target. So even for the very distant sensors where you have to factor in the time of flight of the analog measurement in the fiber, we're still very comfortably within that 2 millisecond horizon, effectively from sampling to output. So it's comparable with traditional measurement schemes in that way.
Great, thank you for that. And another one here, which is probably a similar question actually, or inspired by the same kind of question, was about, you mentioned the drawbacks of distance protection schemes. So, you know, where you've got a complicated feeder with lots of different terminations, you could have, you know, a fault contained in different branches. So how is it that we're able to do the synchronous location and see if it's one branch or another? So could you go back over the advantages versus distance and how we enable that kind of line differential protection scheme again?
Yes, of course. So as you've said, Saul, The drawbacks to distance protection, particularly in this application where you have complex multi-terminal circuits, is that it will have some ambiguity on fault location because there's a resolution associated with its location of the fault as a distance from the measurement point. And that's why operators generally want to use differential protection, because if you can monitor the current into and out of each one of those terminals or each one of those zones, then you know with very high confidence whether a fault has occurred in that section or outside of that section. And as I've said, differential protection obviously is what the operator wants to install, but it can be overly complex with traditional methods because you have to have multiple hardware devices, multiple protection relays distributed over a wide area to measure the current into and out of each zone. And then they're all communicating back and forth via digital telecoms in order to compare measurements all the time and then decide, has a fault occurred inside that protected section or not? Now, because we strip away a lot of that supporting infrastructure and we just use the optical fiber to bring back those measurements to a central location, it's very simple to install a sensor and basically create those protected zones along that fiber. As to how we synchronize those, that's to do with the known time of flight of the measurement in the fiber. So when we install a system, we can very accurately calibrate the distance that each sensor sits along the existing optical fiber. And knowing that, we know very accurately how long it takes the measurement to travel from each sensor back to a central location, which allows us to then bring each waveform measured into relative sync, so that then it's very easy to perform the standard differential protection algorithm on each pair of CTs on each protected zone in order to determine whether the fault has occurred inside or outside of that section. Hopefully that makes sense.
It certainly does to me, but I've heard this a few times before, so I'm not the right person to respond, but yes, of course. Now, that's actually prompted some other questions. So let me sort of jump to that one, Neil, which is, okay, if you zoom out from this, you're giving some examples here about a feeder which has got several branches and sort of, you know, the fault could be contained in different branches. So you've got overlap and underreach problems. We get that. That's been explained. The question then that was prompted is, well, okay, how do you take that into other domains where you haven't got necessarily multiple feeders, but you maybe have a very long feeder which requires breakdown into multiple zones. So you've got this sense of multipoint. Perhaps if you could cover that a little bit, because one of the questions here, for example, was, okay, is this applicable inside of a substation where you're doing multi-point differential protection and you're basically instrumenting lots of bays and you're doing line differential protection from centralized busbar protection or trafo protection? So, you know, multiple schemes.
Yep, that's quite right. So it's a very flexible scheme, and really anywhere you have access to optical fiber is somewhere that you can splice in one of these sensors. So while I've been covering more of the wide area or complex multi-zone, multi-terminal circuits over wide geographical areas in this presentation, you're quite right that inside a substation we can also perform many measurements inside quite a dense area. So that's something that we've done with another transmission operator in Europe, is we've done a busbar protection scheme. So a very similar scheme, but on a much smaller scale, essentially, inside a substation. So as Sol's just suggested, what that involves is providing these passive current measurements on every feeder to that busbar inside that substation. And then we can centralize all those in a single unit and perform a combined differential protection algorithm on all those feeders to determine, has the fault occurred within that busbar zone or outside of that zone, and inform the protection scheme accordingly. We do have a case study for that system also on our website, so I would encourage anyone who's interested in the kind of substation instrumentation architectures to have a look at that as well.
Okay, thank you, Neil. And then, sorry, but these are all sort of like following one from another. So another question here is about, okay, if you've got now a sort of differential protection scheme, could you just repeat or explain, perhaps in better words, the distinction between instrumentation, where we're informing the protection scheme how to respond more discreetly to a fault, as opposed to what you just said about actually running an algorithm which is deciding if we trip a breaker or not, because that's two very different applications, right? I'm sorry, I think there's a delay on the line here. We might have lost Neil.
Sorry, guys, I was on mute. My mistake.
You had me panicking there, Neil. Thank you.
It's
So,
the perils of using Zoom
okay.
for these things.
Yeah.
Sorry, so let me start again. So the nice thing is that the two case studies that I've mentioned both nicely cover the two different approaches that you're talking about, Sol. So in one of them, we're simply providing instrumentation to deliver measurements to traditional protection relays. And in the other, we're actually performing a differential protection algorithm on board our device. So the first one is the one that I presented during this webinar, which is the one you can see on the screen just now, where with a major TSO in the UK, what we're doing is we're providing the instrumentation and delivering that to protection relays. So in this project, we're picking up 3 measurements of current, or three phase locations, so 9 current measurements in total over an area of 50 kilometers. And we're providing 61850-9-2 sampled value measurements to the process bus, which are then being picked up by each one of these relays, and they are each performing the same differential protection algorithm to show that they can work together with our system in order to run that protection scheme. Now, in the second application that I just talked about, where we're performing centralized busbar protection inside a substation for a European TSO, in that application, we're performing the protection algorithm on board our Interrogator unit. So on board this device you can see here, and that's actually outputting the trip signal. And we can do that either via a dry contact on the rear of the device for legacy systems, or we can use a 61850 GOOS message to deploy that trip signal as well. So we can do either approach, and we're very flexible as to how that's deployed.
Okay, thanks. I think you've actually started to anticipate one of the next questions, which was that, it just so happens that what you're talking about are great examples of how you could start using 61850 if the operator, has the ability to subscribe to that sample value stream. So if they do not, and most do not, we recognize that as a company, what are the output options from that interrogator if we're not speaking digitally, for want of a better phrase, Neil?
Yep, of course. Well, the main one I would say is using a dry contact to perform the trip, just like a traditional protection relay would. So that's very easy for us to perform, and that's available as standard. We've also been asked for really various different digital outputs, and we're very flexible about that. Our in-house software team is very capable of either switching between different supported formats, or even supporting new formats if we don't currently do so. So we can be very flexible in that regard. And we've even been asked by some customers to provide, for instance, full analog waveform outputs, which is not something we necessarily do as standard, but it is something that we can do, which would just result in, essentially, we would be providing a remote analog output of each CT at the local substation. So we can really do anything that's required in that area.
That's great, thanks. Okay, and then the last one here, and I apologize to everyone, this is blatant shameless sales and marketing happening for you. But of course, the other application here would be, because someone was asking about cable fault detection. So the idea of, being able to distinguish zones in terms of what's using overhead line and what's using underground or perhaps buried cables. It's not so much a question for you as to point out that we have actually covered this one, so cable fault detection and how you discriminate between overhead and underground faults in a separate webinar. It was 2 months ago, and we've still got recordings of that, and those can be made available to people if they've got a specific requirement in terms of cable fault detection. So Neil, I'm not going to make you go through that one again here, because the content is available in that, and we've actually covered that 2 months back in a separate webinar. But clearly it's another example of a different way to apply the same concept of how you could use this technology to do multi-zonal protection and distinction between, you know, different types of conductors, and therefore to, you know, make the response to a fault a bit more targeted. Now, last question here, then I think we should probably wrap up for today, just so we keep on schedule here. There was a question about, okay, could you just explain again, this is going back to the concept of being able to handle multiple schemes and multiple different sort of protection algorithms in a substation. So the single or same interrogator can handle all the algorithms of all the other protection schemes simultaneously. Is that the right way to understand it? So that question is going back to saying, you know, can we do trafo differential, busbar differential, RAF protection all combined? Which is probably more than what you were describing, which was saying, no, what we're doing is centralizing a simple line differential busbar protection scheme to illustrate that it's possible.
Yes, certainly we can deploy kind of custom or specific protection algorithms on the interrogator. But of course, the power of the system is really in delivering all those measurements centrally to devices whose job it is to do that anyway, like protection relays. So it really saves you from having to deploy protection relays at every end of this scheme, you know, because you're providing all those measurements centrally to that protection scheme. As I say, we can certainly deploy particular instances of protection on the interrogator, and indeed we have done in the past, as evidenced by some of the case studies I've talked about. But part of the power of this system is that it uses the 61850 algorithm in the way it's designed to allow that interoperability of multiple different systems. So we can work with the protection relays from all the trusted manufacturers like GE, like APP, like Schweitzer, to allow them to protect a wide area or a multi-zone or multi-terminal system better.
Yeah, and for what it's worth, just to add something to that from me, Neil, as a commercial answer to that question, what we are bringing to the market with these systems is, you know, a new technology from a young and very flexible and responsive technology company, where we're saying, look, we can provide more real-time or synchronous visibility of a lot of assets, and then aggregate all that information, those feeds together into one simple feed, because that unbottlenecks some of the challenges that people have with having to bring together so much synchronous data to make well-informed protection or asset management decisions. And I'm making that point because we are there to complement and enhance the protection schemes offered by a lot of the standard, you know, major OEMs that are out there. We're not trying to replace people's relays and compete with them and do some sort of relay replacement program, but we can obviously add more software functionality to our interrogators when the customer challenges us to do so. And the case study that Neil referred to there, which is, if you see on our website, they'll application notes about centralized busbar protection with Statnet, the TSO in Norway, talks about it. That was a response to a specific challenge from them, who said, can you also do this, because we'd like to know that this is viable as a backup or shadow scheme, because they can still operate even when there's a partial outage, because we don't lose sync. So it's not the normal thing, it's something that we can do as well, because the processing bandwidth and the power is there in the system. Would that be fair to say, Neil?
Yes, definitely, that's correct.
Now, that said, I'm keeping an eye on the clock here, and I noticed that's taken us to about 1:45, which is normally the time we stop these things, and I'm not seeing any more questions coming in. So if I may, I'm just going to recap here on a few bullet points and housekeeping notes here, because normally at the end of this thing, I want to remind people that for those that registered and couldn't attend, and for those, thank you very much, who were able to give us their time and listen in today live, we've been obviously already talking to registrants and registered participants already in the run up to this, and afterwards we'll send you some follow-up thank you emails and a link to the recording of this in case you want to look at it again. Again, a lot of the information here is actually referred to in the application notes, case studies and white papers that you'll see out there on our website. There's actually a white paper on us which is live on T&D World at the moment that's probably worth looking at as well, which touches on a lot of these wide area, multi-point and multi-zone instrumentation schemes and potential that we have. And again, we'll try and, I think we've summarized all the Q&As here, but after this, we always review ourselves and check on these things and see if there's any requirement to sort of feedback and share Q&As with people. If we didn't give you a good enough answer just now, and it's provoking more questions or it needs a more in-depth explanation, do let us know. You can contact us on the information points you can see here on our website, or through the info or sales links on our email. You can get in touch with us on our LinkedIn feed. Do come back to us with more questions if we haven't answered here, or give us permission to get back in touch with you using your email address for follow-up conversations afterwards. It very often inspires thinking that we then have to explain again in the context of your topologies and how you work your systems, but we're very happy to do that for people if that's of help. So now typically what we'll do is say thank you everyone for listening in. Neil, thank you for the presentation and the clarity of the explanation. We're going to keep the line open for a couple more minutes because sometimes people have questions that then pop up, and then we can manage them. But in the meantime, thanks everyone. Appreciate your time and your participation today. And I hope that we'll be able to join us next time round, because we, if you look at our website, that's Synaptec, that's synapt.ec, you'll see under events, there's a whole series of scheduled events where we'll be speaking at upcoming conferences like IEC 61850. We've just done grid asset management, and then of course we've got webinars planned every month through until the end of this year and beyond, where we're covering more themes like centralized busbar protection indeed, and also some other applications which are more in the realm of condition monitoring and asset management. So do look out for those. And again, if this didn't quite fit the needs or the inquiry you had, do get back in touch with us. So thank you very much and have a great afternoon, and thank you for listening to Synaptec, and we'll talk to you very soon.